Very good morning to all. So last class we discussed about the architecture about BIU and EU. So BIU is for fetching an instruction, and EU is for decoding as well as executing. Okay. So now let me start with calculating a physical address. So calculating a physical address. So we know that we have a default segment registers. So these are the segment registers. We'll be calling as a segment based registers also. It will store the base address, the starting address of that particular segment. Okay. So this is your physical address calculation. So the physical address calculation is segment register. So segment register, in this you may get any one among those. So based on the processor currently executing which segment. So based on that, we can even have a core segment, stack segment, data segment, or extra segment into 10H plus an offset register. Now tell me, so which one will be constant, which one will be changing the value? Is it an offset register will be changing, or is it a segment based register will be changing?
Offset register.
Yes, offset register will be changing. It will be incrementing if it is an instruction pointer, and if it is a stack pointer also it will be incrementing, and the others will be based on the location. It will be placing those values. Now let me go for data segment and offset registers. So if I am selecting a core segment, the corresponding offset register will be IP. So this is our concept. So if I am selecting a core segment, then the corresponding offset register will be IP. So I've selected an IP. So the core segment is a segment starting segment address. So inside a memory, we'll be storing inside this register called a segment register, and these are all the segments. There we have a code segment, stack segment, data segment, and extra segment. So whenever we are selecting any segment, we need to select the particular offset registers. Now, so this is a 20 physical address generation. So in order to calculate a 20-bit physical address, it is generated by adding 16-bit contents of segment register with a 16-bit offset values, which is stored in a corresponding default registers. It may be either IP, BX, SI, DI, BP, or SP. So different segments have a different default registers for offset. For example, if we go for an IP, is a default offset register for a code segment. Okay. So now BIU always appends 4 zeros automatically to the 16-bit address of segment register. Okay. So how it appends means it internally performs a left shift operations 4 times. Okay. So it internally performs left shift operation 2 times, and in the lower 4 bits it will be occupied with the 4 zeros, which automatically converts that 4 the 16 bits to 20 bits to make it a 20 bit, because it knows the starting address of a segment always ends with a 4 zeros. See here, whenever we are going for memory segmentations, we are segmenting, right? So we are partitioning some location to the end of the locations, it comes to one segment, like that. So whenever we are going for a segmentation, the starting address lower bit should always be ended with 0. Okay. So like 1 2 3 4 3 4 0 H. Okay. So 1 2 3 4 0 H is append. Let us consider this is the starting address for a code segment. Okay. Next 1 1 6 8 9 0 is the starting address for data segment. So always it has to be ended with 0. Why? Because we are using what? Zero automatically we are appending in such a way that design has to be done. It has to be ended with 0. So in order to do that, we'll be multiplying with 10. I will be discussing that. So see here. So first this is your segment register. So what we have done a left shift. So you will be getting 4 zeros. Next, this one and the 16-bit offset registers, both we have to add, so that we'll be getting a physical address. Okay. Now let me show with an example. So before going for an example, so see here, this is your memory location where you will be having a 4 segments. And I said, no, what is the use of an offset register means, from in this location, if the processor wants to access this, then this value plus if you add the start address, then you can go to this particular location. So So I have just given one example, like chapter. The starting chapter of an will be give page number will be given in a code segment. Inside that chapter, if you want to go for a particular page, that page number will be present inside an offset register. So if you add, then you will be going to a particular location. So we know that for code segment, the offset register that we are using is an IP. For stack segment, the offset registers will be SP and BP, and for data segment it will be SI. So there will be more for data segment. It can be a SI, source index, it may be a destination index, or it may be a BX also, which is one of the general purpose registers, BX, that we'll be discussing. And ES is a for ES segment register we'll be using offset register as DI. So by seeing this diagram, you must know a very clear idea about what is a base register and what is an offset register. Now coming to this, the by this you should know about how to calculate. So this is your BIU, where your segment registers will be present, and this is your memory where you are going for four segmentations. So you will be having four. So what are those four? Core segment, data segment, extra segment, and stack segment. Okay. So each segment, concentrate now, each segment will have a size of 64 KB. Okay. So this is your 64 KB. This is your 64 KB. So here, so what is that size? Why this size is selected? I will explain later, but try to understand. So this is your 64 KB. Okay. So here, this is the starting address. So this is your segment, code segment, where you have a starting address as 34BA0. Okay. But as the register size is only 16 bits, this 4 bits will be stored inside a register. In order to calculate this 0, internally system will perform a left shift operation 4 times, so that this 0, you can get this 0. Okay. Now you can reach to this. Now if you add an offset, then from this, if it wants to go to this particular location, then we need to go add an offset, so that we can calculate our physical address. See here. So let us consider an example. The following example shows in code segment and a instruction pointer. Now we want to calculate a physical address. So if you add this, you will be getting a physical address. In that physical address, the processor wants to fetch this instruction and wants to execute this. So for that, so this is your code segment. So in this you have 34BA. So it has to reach to this. Okay, 34BA, and it has to convert this 34BA to 34BA0. For that we are doing left shift operations 4 times. Okay, into 10 we are doing. Okay, and IP. So and IP, so plus if you add this, you will be going to that particular location, this location. Okay, so for that what we are doing is we are inserting a hexadecimal 0H in the lowermost digit. So here 34BA0 is your one that we calculated. Then we are adding with the offset value, which is 8AB4. Now concentrate ma. See here, 0. We are doing here not a normal addition. We are doing hexadecimal. So we are doing hexadecimal addition. So if you are getting greater than 16, you should perform a division operation again. So see here, 0 plus 4, you will be getting 4. Now tell me, so let me write A, B, C, D, E, F. Now tell me what is the value for A? 10, 11, 12, 13, 14, 15. Okay. Now what is A here? A plus B. So A is 10, B is 11. So if you add, what you will be getting? 21. Is it a 21 is a valid number in a hexadecimal?
No.
No. So you need to go for 16. We need to divide this. So if you go for, so 1 and remaining is what? How much is remaining?
5.
5. So you, as whenever you're doing, you need to go from bottom to top. So you will be getting 5 as a result here, and 1 will be carry, and 1 will be carry. Okay. Now tell me, what is how much if you add B is 11, A is 10 plus 1. So you'll be getting what? How much? 20? Is it 21 or 22, including carry?
22.
So 22. So if you do, what you will be getting? 1 and 6. Okay. So if you go, so then what you will be having? You will be having 6 here and 1 will be placed here. Now tell me, 8 plus 5.
14.
14.
13. 13. 8 plus 5.
So 13 is represented in hexadecimal as D. So it is mentioned as D. Next 3. Okay. So you should know how to do a hexadecimal addition. So whenever it is exceeding greater than 16. So I should even, is it 16 is a valid number in hexadecimal, or we should go for division again? The 16 is a
So
valid number.
we should go for division.
Yes, why? Because it starts from 0 to 15 only. So even if whenever you're going for addition, if you're getting 16 means again you need to go for division for calculating. So this is an addition. So based on this, this is an address where a processor wants to fetch an instruction. So it goes to this address called 3D645, and whatever the instruction which is present here will go for fetching that particular instruction. Okay. So now let me give one more example so that I will see who will answer. So let us consider CS is equals to A to EF, and the corresponding offset register IP equals to 1 to 3A. Calculate the physical address. Calculate the physical address. A to EF is a code segment and the IP is 123A. Calculate the physical address. Huh? Tell me fast. What is the physical address? So you will be getting, after doing this code segment left shift operations 4 times, you will be getting
A4116.
A4
116.
1 116. Anyone?
A412A.
Yes. Why you will be getting 6 in the least significant bit, ma? See here. So you will be having code segment as A to E F, and when you do left shift operation, that is nothing but you're multiplying it with 10, so you'll be getting 0. And in an IP we need to add this IP address to get us offset register, so to get a physical address. So 123A. Okay. So if you add here as it is 0, you'll be getting A. Next is what? F is what? F
2.
is 15. So 15 plus 3 is how much?
18.
18. So if 18, if you do, you will be getting 1 2. So 2 will be placed here, 1 will be placed here. Next, after adding, you will be getting 17. So 17 means if you go, you will be getting 1 1. So 1 has to be placed here. So you will be getting A412A. How many done correct, ma?
Oh my god.
Others?
I also got.
Okay. Just give a message in the chat box if you have done yes. Okay, so in this way you have to calculate a physical address, but in some cases they will be asking to represent in binary. They will be asking to represent in binary. In such case, you should convert this hexadecimal to binary. You should convert this hexadecimal to binary. See here. So this is one more example. So this is your A4FB is your code segment. Let us consider this is your offset. If you add, you will be getting this 20-bit physical address. Okay, you will be getting a 20-bit physical address. Now, in some cases, it will be asking to convert to represent this physical address in a binary representation. In such case, you have to convert individually. So the A is what, ma? Let me write first the segment register A4 FB. A is what? A is represented as 10. So 10 in binary will be represented as
1010.
1010. 4 as 0100. F as F is which number?
15.
15 means all ones. Next, B is 11. 11 means 1011. So you have to represent like this, and you have to clearly show first left shift. So this one will come here. This is your first left shift operation. So this one will be coming here, and this 3 will occupy, and this 0 will be coming in this position. Next 100, this one will be coming in this position. Next 111, this one will be coming here. Next 011, and in the left out bit you will be placing 0. One time completed, one time over. Next we need to do for second time. Okay, so if you do for second time, so this 0 will be coming here, and you'll be having 100, and this will be coming here. Next 001, this one will be coming here. Next 111, this 0 will be coming here. Next 110,
0.
0. Second time completed. So third time. So next is 10, this one has to come here. You should represent in stepwise. Okay, so third time completed. So then in this place you will be getting as 001, this 0 will be coming here. So like that, when you represent completely, these bits will be coming in the hand. In the final bits you will be getting all zeros. Okay, so in this way you have to represent, and finally you will be getting as A4 FB0. So whenever they are asking in a question to represent in a binary, then you have to convert that. So after converting, this is your in this example, this is your segment 1000. So 1 is represented as 0001, and 0 is represented as 4 zeros. This is already done, this process, and after completing this process you will be getting as 0001, 0000. This is, so this is a one that we have done after completion of 4 left shift operations. The remaining empty bits will be ended with 4 zeros. Next, this is your offset register. So if you add, you will be getting. Now if in order to represent this in a hexadecimal representation, tell me by seeing this what hexadecimal address, 20-bit physical address it is representing. What is this hexadecimal representation? Tell me, ma'am. 0001 is what?
1000.
100 to 9,
9, ma'am.
yes, 29H means what? The processor wants to fetch an instruction which is present in this address, okay? So you have to represent clearly stepwise. So finally you will be getting as 1010, and this we will be getting as 1000. So 111 ended, the last 4 bits will be ended with 4 zeros. So now, so this is your calculation of physical address. Is it clear, everyone? Is it clear?
Yes.
Ma'am.
Okay. So next, we'll be going for register organization. So we'll be going for register organization. So in this, we know that there are general purpose registers, there are segment registers, and we have a flag which is used for flag, also called as program status word. Okay, also called as program status word. Why? Because what is this flag indicates, what it represents is, after completion of some operations, arithmetic and logical operations, in the result what the result is, whether it is a negative number or whether it is a what it shows the status of a result. Okay, so the entire will be representing in flags, and we'll be having what, we'll be having a stack pointer, base pointer, source index, destination index, instruction pointer, and these are all called as an offset registers. And these offset registers you try to mention whenever you are representing. We have an offset registers, we'll be dividing into two types again: pointer offset registers and index offset registers. Okay, you can mention like that. So pointer offset registers means stack pointer, base pointer, instruction pointer, you will be getting 3 pointer registers, offset registers. And index registers, you will be having a source index and destination index. Okay, and general purpose registers, these are 4 general purpose registers: AX, BX, CX and DX. And no, so AX, BX, CX, DX is of size 16 bits, and 16 bits can be divided into two 8 bits. So this is 8 bit, and this is of size 8 bit. So AH indicates the lower order 8 bits from 0 to 7, and the AH indicates the higher order bits from 8 to 15. Okay, so 8086 have an advantage that you can access a instead of accessing 16 bits, you can even access 8 bits also at a particular time. Okay, so even this is also BH indicates higher order, lower order, and we'll be discussing one by one. Okay, so now let me start with this. So just now I said no, so these are the general purpose registers, and general purpose registers will have, only general purpose register will have an advantage of dividing that 16 bits into 8 bits, like higher order bits and lower order bits. And we have a 2 pointer registers, stack pointer and a base pointer. We have a 2 pointer registers, and we have a 2 index registers called a source index and destination index. And we have a one more pointer called an instruction pointer. This all 5 comes under which registers, ma? Comes under
Offset registers.
yes, you should give a side heading as a offset registers, and you should mention will be of two types. One is a pointer registers and the other one is index registers. And coming to segment registers, we know that this, what is the use of the segment register, what will be stored inside a segment register?
Base address.
Yes, the starting address of a segment will be stored inside a these segments. And this is your status register. So status register is nothing which is nothing but it shows the status of a result after performing a arithmetic and logical operations. It stores the status of a result. Based on this result, the processor will have an idea so what is the final result. Okay, so let me start with the general purpose registers. Okay, so these general purpose registers, we have AX, BX, CX and DX. We'll be discussing one by one. So coming for AX, a 16-bit register can be divided into two 8-bit registers. So these are higher order and lower order. So this you should mention as it is from 0 to 7 and from 8 to 15, from 8 to 15. So if it is given in the code like move AX comma BX, then what it indicates, the contents of BX will be moved to AX. Means let us suppose AX, let me give some value. So as it is hexadecimal, I want to represent the data also in a hexadecimal. So 1 2 H and 3 4 H. 3 4 H is present in AX, and in BX let us suppose we have 1 2 1 H and 2 4 H. Means what, this contents will be moved here. Now 12 and 34, what is this, 34 will be replaced with 21 and 24. So this is your move. Okay, so let us consider, even I can say as move AX comma, let me clear now, move AX comma 1 2 3 4 H. Okay, means what, this will be moved into this contents. Is this correct, ma? Let me write move AX comma 1 2 H. Which one is correct? First one or the second one? Which instruction is correct? First one or the second one? See here, ma, you should know before that what is AX size. So AX is a 16 bits. The size of this register is 16 bits. Okay. So if it is a 16 bits, how much I am giving? It is represented in hexadecimal. So you have 1, 2, 3, 4. So what is this 1, 2, 3, 4 if you add? So as it is a single digit is represented with 4 bits in a binary in hexadecimal representation. You are giving 16 bits and you are placing inside a AX. But in this case, are you giving 16 bits?
No, ma'am.
How many we are giving? 8. Okay. So when you are going for 8-bit, it should be specific. So will you want to go for higher order or will you want to go for lower order? It should be specific. Means if you are going for 8-bit, you should specify that move to AL, comma 1 2 H. Then it moves this to this AL. Are you getting my point? So it depends upon. So you should know about AX is a 16-bit register, AH and AL is of 2 8-bit register. We can access separately by, if you want to move this 12 to AL, then we can give 12 and you can specify you want to move this to lower order or you want to move this to higher order. So this is specially for general purpose register. AX is it's called an accumulator, and BX is your base register, and CX is count register, and DX is a data register. These are all used for storing temporary results. And see here, ma'am, try to understand, this is very important. So here in an accumulator, so we'll be using this as an accumulator, and everyone knows what is an accumulator. So one operand will be stored inside an accumulator. Next, this is used for performing all the operations, whatever that you want to do, you will be using an accumulator. Next, coming to BX, while representing a what, where we used BX, ma? Can anyone? Where we used BX? See here. Okay. So in our data segment, BX is acting as which register, ma?
Offset.
Yes. Okay. So first role of BX register is it will be acting as general purpose register. Okay. So it will be acting as a general purpose register. Means what? For storing some operands, it will be acting as a general purpose register, plus it will be even acting as a base register. Means base offset register. Means what? For which it will be acting as a base register is for a data segment. So this will be along with the general purpose register, it will be acting as a base offset register. Next is what? A CX. This will be, first is it will be used in general purpose register, plus it will be used in as the name is, it is count. Means what? In a loops, whenever we are in a program, whenever you are writing a loops, in such case internally to store those operands, we'll be using a register called CX register. So count register is used especially in iterations like loops. So whenever you're doing left shift operations, all those, along with general purpose register, we even use inside a loop, so those operands to store, we'll be using CX register. And DX register is along with general purpose registers. These are used for storing IO instructions and multiple and division instructions. So this is about 4 general purpose registers called AX, BX, CX, and DX. Okay, CX is, if I ask CX means other than general purpose register, CX is used for storing the loop operands. So storing a loop operand. So when I say about DX means along with general purpose, it will even store the IO instruction operands and multiple and division instruction operands. Okay. Now let me go for segments. So we have done with the general purpose registers. Now let me go for segments. Okay. So we have 4 segments. So what are those 4 segments? Code segment, data segment, stack segment, and extra segment. So code segment is the space to store a program that will be executed. The program will be stored inside a code segment. The data will be stored inside a data segment. Inside a stack segment, I have given a complete explanation about where we'll be using a stack. Okay, so special space to store information needed by a microprocessor to execute subroutine or interrupt the service. Yes. So whenever there is a subroutine call, it has to stop its main program execution and it has to jump to that particular subroutine call. So whenever it is going to that subroutine call, what it has to do, ma? It has to,
First it will clear and then
yes, it has whatever it is jumping. So this is your main program, and you'll be having an instructions. And let us consider here you have a subroutine call. So these are your instructions. So this is your subroutine call. Okay. So before jumping to the subroutine call, the next instruction address will be pushed inside a stack. Okay. So for that we'll be using stack. So see here, special space to store information needed by microprocessor to execute subroutine or interrupt service. Okay. So whenever we will be going for push, next whenever it returns from this, it pops so that it identifies that it has to start from this particular address called 500. So this is about stack. Next is extra segment is what? So when data segment which is given is not sufficient, then we'll be going for storing a data segment in a extra segment. Same function is same as a data segment. Okay. So these are all about segments. These are all about the segments. Next, coming to instruction pointer. Okay, so instruction pointer register. Yesterday also we discussed about this register which stores instruction address to be executed. Okay, so each time instruction is fetched from memory to be executed in processor, IP content will be added so that it always shows to the next instruction. Okay, so this is your content. So let me show. This is your content. Okay. uh, Next is one. So let me show in this. So this is your content. Okay. Next, in this, what is this? Indicates the code segment. Okay. See, code segment will be having starting address as 12340H. Okay. So now if it wants to access this first location, if it wants to access in sequence, then we need to go for IP. So IP will set to 0 first, then it will access. Next, IP instruction pointer will set to 1. Then if it is 1 means this 1234 plus 1, it will go for the next address location called 1234H. Next, why? Because this is a code segment. The program will execute in sequence one by one. So the value will be changed in instruction pointer. So 0, 1, next it will be incremented to 2, next it will be 3, next it will be 4. So that you will be getting as 4, 1, 4, 2, 4, 3, 4, 4, like that. Okay, so it will be like in accessing in this way. Okay, so that's the reason instruction pointer will be incrementing. And when we'll be changing this instruction pointer branch instruction, the instruction pointer content will be loaded with a new value which is a branch. So what we are doing, we are executing in sequence. So but this sequence will not work if there is a branch to this particular location called 500. Then this IP has to be it should not increment, it should place this value called 500, so that if you add this base register with 500 with offset value, then it reaches to this particular location. This is your instruction pointer. Now in index register and pointers. Okay, this registers is used for storing the registers is used for storing the shifting value for memory address location. See here, we have a stack pointer and a base pointer. Yesterday I discussed about what is a stack pointer and what is a base pointer, right? So can anyone tell me what is stack pointer and base pointer? Stack pointer is used for
top of the stack,
Yes. So
which
when
refers
you
to top.
yes, which refers to the top of the stack. When you want to access the top of the stack element, when a processor wants to access the top of the stack element, then the starting address of the stack segment plus a stack pointer, if you add, we can reach to the top of the stack. But instead of that, you want to select used for fetching the data in the data segment base pointer. So it can be used for fetching any data. So if you want in any data, if it wants to fetch an instruction, this base pointer is used. Next we have a two called a source index and destination index. So source index is it contains an offset address for source operand in data segment. So destination index one, it contains an offset value for destination operand in data segment.